We learned that the derivative is the instantaneous rate of change, and it is also the slope of the tangent line. And that second definition of slope of the tangent line is our focus for this lesson. We will define derivative as the slope of the tangent line, and we'll be looking at it from a graphical perspective. So graphically, we can say that the derivative is interpreted as slope. In other words, f prime of x, which is our notation for derivative, so that's the derivative of f of x, is the slope of the original function f of x for all x. You might remember earlier in this unit, we introduced this idea of slope graphically by doing a matching activity. So we looked at an original function and then tried to match the graph of the slope of that function. So that's what we'll be doing today and learning a tool to analyze that slope a little more carefully. So the idea here is that the derivative value of f of x becomes the function value of f prime of x. That's a pretty formal way to say it using those new terms of derivative. So let's say it in a more simpler way with terms that you're a little more comfortable with. So in other words, the slope value of f of x becomes the y value of your f prime graph. These next three statements are basically the rules of behavior of any function, and we organized these thoughts into a table on a few notes ago that we had, but let's remind ourselves what is happening with the function and the result in the derivative graph. So if our function is increasing, which means it has a positive slope, our derivative, which is slope, is going to be positive. And when we graph that derivative or slope, that y value is going to be positive or above the x-axis. So the second statement is the complete opposite. If your original function is decreasing, then your slope and your derivative are negative, and therefore your graph of your derivative or slope, your y value is going to be below the x-axis because it is negative. And then the one exception to those two is that sometimes you have a function that is constant, or you can think of that as being horizontal. If that's true, your derivative is going to be 0 because the slope of a horizontal is 0. And therefore, when you graph that slope or derivative, you're either going to touch down on the x-axis at a point or actually cross the x-axis, depending on if you alternate between positive and negative slope, or if maybe you have a positive slope, a 0 slope, and then a positive slope again, and that's when it would only touch down. And these rules, I think, will make more sense when we put it in the context of some graphs. So we're going to work through some examples of graphing a function, analyzing its slope, using a sign chart, and that is the tool that I mentioned earlier about how it's going to help us analyze that slope a little more carefully. And then we're going to take the information from the sign chart and graph the derivative function. So we have a few examples in this section. We're going to work our way from a really basic example to some more interesting functions. So our basic function is f of x equals 2, and when we graph that, it is a horizontal line. So once we have our graph of f of x, we need to make a decision that describes the behavior of that function. And this function doesn't do a lot as far as changing behavior. It has one behavior for all of its domain, and that is that it's constant. So when we look at our sign chart is going to compare the behavior of f of x to f prime of x. And we're actually going to look at some other sign charts later in this unit that compare maybe the first and second derivative with the original function, but that's something that we'll build upon. So today our focus is just f to f prime sign charts. So now that we decided our function is constant, we'll write that up here, and then we'll translate it to what our derivative function is down here. So I have my constant behavior of f of x. I know that the relationship is that when f of x is constant, my derivative function is 0. So I make that translation down here to describe the behavior of f prime. So these arrows here are not necessary for you to put in your sign charts. I'm just showing you your train of thought. So you graph your function, you come over, you describe the behavior of f of x, translate that down to the behavior of f prime, and then we'll take that information and actually graph f prime to finish this example. And since I decided that my f prime graph would be 0 without any change, when I went to graph it, that y value is 0. So it ended up being the x-axis or the function y equals 0 for my derivative. Let's look at the second example and hope it's going to be a little more interesting than the first, but nothing too complicated. This time I have a linear function negative 2x. I know that my slope is negative. It has a y-intercept of 0, so it'll go through the origin. It'll be decreasing from left to right. So notice I only put the arrow on the right side to show you that it's a decreasing function. We'll take that information about the behavior and go ahead and start setting up our sign chart for f to f prime. Since I decided my f of x function is decreasing, I would think about that relationship between f and f prime. When f is decreasing, f prime is negative. Remember, that also means that my f prime graph, is going to be below the x-axis. So you're welcome to write out negative and below, but as our sign charts get a little more complicated with more changes, it might be faster for you to just write a negative sign and a B for below. After making that translation down, getting negative below for f prime, I'm ready to take that information and graph my f prime graph. I know that it's negative below all the way across. There was, again, no change in our function. So I also happen to know, since it's a linear function, the slope was specifically negative 2 throughout that line. That slope does not change. So I have a horizontal line at y equals negative 2. So remember, the slope of this function, your original function, becomes the y value of your f prime derivative function. And only when it's linear is it going to be a horizontal line like we've seen in the last two examples. And the next couple examples, you'll see that the functions get a little more interesting as well. Our next example is our friendly parabola. And notice, again, I only put the arrow on the right side because I want to think about reading that graph from left to right. So that's where it's going to extend out. So if I look on the left-hand side of our function, I see that from left to right, at first it's decreasing. And instead of writing out the word decreasing, I'm going to use a decreasing arrow because I've got a little bit more to fit on my sign chart this time, and it's just a little quicker to draw a symbol rather than writing out words. This is the first time that I have a change. In my first two examples, the behavior was the same all the way across the domain. But in this function, we have a change at x equals 0, so we'll put a dash, and this you can think about as a number line of the domain, so those are x values. So at 0, it changes from decreasing to increasing. Now that I have the behavior of the function across my domain, I'm ready to translate that behavior down to my behavior of the f prime graph. I know that decreasing means I have a negative slope or negative derivative, which will be graphed below the x-axis. And increasing is a positive slope or positive derivative, which will end up above the x-axis when I graph it. I want to talk a little more specifically about when that change occurred at 0 from decreasing to increasing. What we're actually looking at in our parabola is a horizontal tangent at 0. So we're going to notate those on our sign chart and say that f of x has an HT, or horizontal tangent. And what that translates to down here actually comes from the relationship up top. When our function went constant on that horizontal tangent, our f prime of x is going to be 0 and either touch or cross the x-axis. So we can think of that as being an x-intercept. That x-intercept is a great place, and actually the best place, to start graphing your derivative, because we know we have an x-intercept at 0, so that kind of anchors our graph. Before the 0, our derivative graph needs to be below, and after the 0, our derivative graph needs to be above. And the simplest way to make both of those things happen while still crossing through the x-axis at 0 is to draw a linear function. So just to double check our derivative, we have a function that's negative below. When it gets to x equals 0, there's an x-intercept, and after that, the graph is above or positive. So we'll do one more example of this when we get to class, and below that we're actually going to be going in the reverse order, matching a derivative to an original function. So I'll see you in class.